So now we can summarize the entire CLAHE operator using the earlier adaptive histogram equalization method that we also discussed. So the naive adaptive histogram equalization, we divide the image into bins. Where n is usually 6 or 8. So we have p equal to n square bins. In CLAHE as well, we have the same step, divide I into p equal to n square bins, n square grids. We divide the image into n cross n grid. Then the next step is we compute the histograms, or directly the normalized histograms in this case. In CLAHE, we compute the histograms. In naive adaptive histogram equalization method, the third step is to compute the transformation function, which is the cumulative distribution functions of the histograms, of the normalized histograms. So we would have p such transformation functions. Here we clip the histograms and redistribute. So we call this entire process just as clipping of the histograms by a user supplied threshold tau. On the left, we proceed as usual. We compute the transform values using bilinear interpolation. Here, after clipping the histograms, we compute the normalized histograms. And then we compute the transformation functions using the cumulative distribution functions of the clipped normalized histograms. And then we finally compute the transformed image using bilinear interpolation. Which we have already covered in the previous lectures. So using the pseudocode that we covered for the naive adaptive histogram equalization, and what we discussed, these additional steps in the CLAHE operator, using the same code that using the same pseudocode that we provided for the naive adaptive histogram equalization, we can just inject this clipping step, and that would be our CLAHE operator. So that covers the discussion of histogram equalization and adaptive histogram equalization. And there's one more additional topic as to how do we extend the ideas of histogram equalization to color images, which we'll be discussing very briefly next.